This
Forgot to
conference
do
will
that,
now
so it
be
is
recorded.
recording. So in a nutshell, you know, just to kind of recap, electric flux is the dot product of the electric field and the area vector. It's important to keep in mind that these are both vectors. The area vector is in a direction perpendicular to the plane. We can see that here. And we'd be, you know, having no electric flux if the plane is normal to the electric field, as we've seen here, I guess, in sketch C. If that's sketch A, that's sketch B, and that's sketch C. Jill, make sure that I've answered your question conceptually about electric flux. There's a kind of a neat video that I've posted by a YouTuber that has a weird name, Lassenviren or something like that. And those videos I've posted somewhere in Unit 4 on Unified Classroom. So one of those videos basically specifically addresses this concept of electric flux, which is tough to visualize, I think. Now, if we go to this question number 35 that I did earlier today, it says that we have an electric field. Nope, that wasn't it. It's question 36 right here. The electric flux is given to you in unit vector notation. So 24 units of the electric field are directed right, to the right in the I hat direction. We could say positive X. 30 newtons per coulomb are directed in the positive Y direction, or J hat. And 16 newtons per coulomb are directed in the K direction out of the screen. And we have a 2 square meter section. And so the question then is, well, you know, if specifically that 2 square meter section of a YZ plane, again, this involves, you know, what I would call minimally kind of some three-dimensional sketching. So I'm going to try to do that here in pink. Here is the Y direction, and this is the X direction. Nothing should be, you know, different from what you're used to seeing. And the Z direction is going to be weird, right? It comes kind of out of the paper. I don't know if I'm going to be able to sketch this. You know, one way is to just say that, you know, that circle that I've drawn is in the Z direction coming out of the paper, out of the screen towards your face. And so therefore, the YZ plane is going to be a plane that's in the Y direction and the Z direction. I don't know. I've tried to draw it this way. None of it is really going in the X direction. I don't know if that's kind of clear by the way that I've drawn it. So I'm going to draw this kind of grid on this thing. And so therefore, the electric field that's going to penetrate through that is the component that's directed to the right. That's the part of the electric field that's going to go through the YZ plane, is the electric field that's directed to the right. The electric field that's directed up, this part of the electric field, is not going to go through the YZ plane. By our definition that we made earlier, the area vector of the YZ plane is in the X direction, or the I hat direction. This is the area vector of the YZ plane. And so therefore, if it's to the right and the electric field is up, then the Y component of the electric field is not going to produce any flux. And for the same reason, the Z component of the electric field coming out of the screen towards you will also not generate any flux. So let's go up here to our definition of electric flux, and we're just going to multiply the I hat component of the electric field, which is 24 newtons per coulomb, times the area vector of 2 square meters, and that's going to give us 48. And you can see those funky units, newtons, meter squared per coulomb, and we get 48. That's going to be the I hat component or the X component, 24 newtons per coulomb times the area. Jill, make sure that I've answered your questions. I know you didn't specifically ask about question 36, but I just did that one about electric flux and wanted to use that as kind of a follow-up to the conceptual layout that I did before. So again, this is the only question that I've gotten so far from Jill. Let me know if you guys have additional follow-up questions. Farnaz has asked about question number 53. So let's go ahead and go there. This question says, an electron has charge minus E and mass ME. A proton has charge plus E and mass 1,840 ME. So we want to know the equivalent of a proton volt to how many electron volts. I think this ends up being, a bit of a, I hate to use the word trick question, but an electron volt is a certain amount of energy that it requires to move a charge through 1 volt. That's really what it is. And it has a joule equivalent. So for starters, even though this wasn't kind of asked specifically in question 53, for starters, let's take a look at the equivalent of 1 electron volt. It's going to be the number 1.6 times 10 to the negative 19. Now that number should look familiar to you because that's how many coulombs are in the fundamental unit of charge. And so this question is saying we have an electron of a certain charge and a certain mass. They're saying the proton has the same magnitude of charge, but 1,840 times more mass. So they're saying then a proton volt is equal to what? And, as I said earlier, I'm going to actually have to, I want to look up the formal definition of an electron volt, but an electron volt is how much energy is required to move an electron through 1 volt. If this is an electric field here, and this is 0 volts, and that's 1 volt. By the way, those solid curved lines that I've drawn are equipotentials. Then to move the electron from that 0 position on that equipotential to the 1 position through any path, if there are no non-conservative forces acting, it doesn't, it's path independent. And so that's the amount of energy required to do something like that. So since it's only dependent on charge, the mass is irrelevant, and that's where choice A comes from. But while I am waiting, so Emil has a follow-up question, and Jill is saying, when do we take into account surface charge density? Okay, that's a different question. And then FRQ number 4. So before I answer those questions from Jill and Emil, I want to formally look up an electron volt, make sure that I've defined that properly. Oops. right. Yeah, so it looks like I have that correct. I'm going to change the screen that I'm sharing and bring you to my Wikipedia page. Oh, it looks like you guys are on it with me anyway. So here's the Wikipedia page for an electron volt. And here we can see that it's 1.6 times 10 to the negative 19 joules. But then the kind of more formal definition right here is the amount of energy gained or lost, depending on what direction you're going in, by the charge of a single electron moving across an electric potential difference of 1 volt. So a proton volt, since it has the same charge, is going to have the same value, proton volt and an electron volt, then in that way. I'd never heard of a proton volt before that question. But nonetheless, there we go. Let's go back to Acrobat. Okay, and then let's take a look at, I'm going to do Emil's question on FRQ number 4, and then I'll go back to Jill's question on surface charge density. All right. So it looks like we have 3 electric charges arranged in a coordinate system as shown. They want all the algebraic, all the answers in those terms. On the diagram, draw vectors representing the forces, F1 and F2. So, Emil, by the way, make sure this is the right problem that you wanted me to go over. So since this is positive up here, then the smaller positive kind of lower hand Q here, there's going to be a force here that I've kind of drawn in blue due to that one. I'm going to color code this and make the other one a red one. This is negative, and so now we get force down and to the left. Because of symmetry, we're going to find out, maybe just by visual inspection, because of symmetry, we'll see that the X components will cancel out and the Y components will add together. So if I'm calling the one on the left F2, then F2X is to the left and F1X is to the right. They're going to cancel each other out. The Y components, however, are both in the downward direction and they're going to add together. So I can call that F1Y and F2Y. If the magnitudes of the charges are the same and there's symmetry, so the distances are the same, then, our net force is going to be, these two guys added together or just one of them multiplied by 2. So they're saying determine the magnitude and direction of the total electric force on the positive Q charge. And that's kind of what's going on here in part B. The X components cancel, so the net force is the sum of the Y components. Here's an application of Coulomb's law that we kind of were going over. Let me erase these. We were going over this in our kind of review session after school today. So, here's our net force expression for Coulomb's law, 2 times KQ1 Q2 over R squared. And let's see here where this expression for cosine theta, it depends what we're defining as theta. That hasn't been done in the question. So we want to typically reference, let me see if we can take a look at this. I've written in this work here, cosine theta is D over R. Cosine is adjacent over hypotenuse. So the adjacent side is D and the hypotenuse is r. I think that's pretty clear. Why is that doing that? Give me 1 sec here. I don't know, my pen's behaving a little weird. All right, so we know this is a right angle, and so this is going to be the angle theta here, which is a little bit weird. I'm not sure why I chose to use that angle. You know, alternatively, I could have chosen this angle here, the one in red. But it looks like I chose the one in green because of that statement right there, d over r, where it's adjacent over hypotenuse. I'm still confused why I did that. Nonetheless, let's just keep going. And let me erase this stuff. So now I get 2k times big Q little q, and then because of the cosine piece, and I referenced the green one, I'm going to get this expression for cosine theta, which is going to be d over x squared plus d squared. I used cosine theta, again, referencing that upper angle right here. If I'm referencing the y-axis, then cosine is going to be the y component. And so, you know, I think that's what that's about. That's part B. Determine the electric field magnitude and direction at the position of Q. So B was the hard part. And then in part C, we're just going to use our work from part B above and substitute it in for F. This is, by definition, the electric field is the force per unit charge. And so that's where part C comes into play. And then for part D, calculate the electric potential at the center at the position of plus Q due to the other charges. And, you know, because they're the same distance away, this is kind of another, I mean, I've seen this just so many different times. You know, a series of questions that start with electric fields and then go to potential, and we see like different results. But my point is, in this problem, even though we get a net electric force and therefore an electric field directed downward, the electric potential at that point is 0. There's only these two charges, positive Q and minus Q, at this point P. And so therefore, the distances away from them are the same. Remember that electric potential is a scalar quantity. And so therefore, we're just going to use KQ over R plus KQ over R. One of the Q's is positive, one of the Q's is negative. And so they effectively cancel each other out. And that's where part D comes into play. And then finally, charge positive Q is now moved along the x-axis to a very large distance away. You know, we can kind of assume well, I was going to say that we could assume infinity, but then we see in the next statement that the magnitude of the force on the positive Q charge at this large distance now varies as 1 over x cubed. And this one is I guess new to me here, or at least I haven't looked at it in a sufficiently long time. And my explanation here is as x increases the distance to the charges, r and x becomes similar. So let's take a look at this. X squared plus d squared. Oh, yeah, so let me draw a sketch up here. So as this thing gets really, really big, and so the triangle that I've drawn in green here, we're seeing that if this is R, then this is X. The bigger that triangle gets, the more trivial this distance D is, and R and X are almost the same value. They'll never be precisely the same value, but they do approach an equivalent value, and therefore x squared plus d squared, all under the square root sign, is approximately equal to x. I'm trying to evaluate that here. Hold on. I guess my question is, why doesn't it approach 2x? Because of x squared. Oh, I see. So this just becomes, I don't know why I wrote that, but as this gets really, really big, this becomes trivial. And so we can say that the square root of x squared plus d squared is pretty much just the square root of x squared, which is x. And so therefore, when I go up to my expression and back substitute now that statement, so I have to go all the way back up. We're looking at the force statement, which is way up here. It's way up here in, oh, come on, where we started. And so now x squared plus d squared is just going to be x. So this is just going to be x. I'm not sure what's going on here with the 3/2. I think I'd have to take a closer look at that. Yeah, because when I back substitute that in here, what I'm trying to figure out what happened to the 3/2. It would make sense if it was just cubed in the denominator, but it's not. I don't think it comes from a derivation. I'll come back to that last part, Emil. I'll take a look at it later tonight or tomorrow morning. Surface charge density was Jill's question. So I'm just going to find like a blank piece or kind of an empty part of the paper and go over that, and then we'll call it done. Surface charge density matters. I think you're thinking of situations where we have two spheres, and let's say that we have plus 2q on an insulating stand, and we have another sphere here. Let's call it plus 6q. And if the two surfaces are the same, if the surface areas are the same, R1 on the left is equal to R2 on the right. When we eventually connect those two, either by touching them together or putting an electrically conductive bridge across there in green, we should recognize that charge will flow. If we're talking about positive charge movement, which is kind of the opposite of what we were talking about in class today, charge will flow from the right sphere to the left sphere until we reach an equilibrium in surface charge density. So we can say that the surface charge density on sphere 2 on the right is going to be equal to the surface charge density of sphere 1 on the left, which, if they're the same size, is going to give us both 4q. So we can see then that the right-hand side loses 2 units of charge, and the right-hand side, the right-hand side loses 2, and the left-hand side gains 2. Now, all bets are off if one of the spheres has a different radius. And so we could say then now that if we have a larger radius for R2, and we do this whole thing again. So let's ignore the things that I've written here in green. We connect them. We're still going to have positive charges leave the right sphere and go to the left sphere, but fewer of them are going to come off. And the reason is there's way more surface area on the right. So unless we know how much surface area there is, we could answer this question, but it's going to go down to a smaller amount. I'm going to make up a number and say we're still going to have a total of 8 units. This one's going to go down plus Q, and this one might go up to plus 3Q. But we can see that the difference is much less. They're going to reach the same surface charge densities at a higher number here on the right and a lower number here on the left. Because remember that we can say that surface charge density is charge per unit area. So if the sphere on the right has more area, to achieve the same surface charge density, it can accumulate more charge. Jill, make sure that I've answered your question about surface charge density. I think that, Emil, what I'm going to do is take a look at problem that you asked about 4 part E. I'll take a look at that tomorrow morning when I get in and talk to you about that or send an email out. All right, that's it for tonight. I will see you guys tomorrow if you have any questions. Otherwise, see you on Friday.